Okay, so yesterday we were speaking of collecting different kinds of data. Okay, as I said in statistics, the idea is that you're going to collect data, you're going to organize that data, and you're going to analyze that data in order to draw conclusions. So we're going to talk today about analyzing the data that we're provided and, looking at some of the values that we're going to use to eventually draw some conclusions. So let's begin with measures of central tendency. And these are ones that you should have studied before when you did stats in one of your previous classes, whether in, Algebra 1 or earlier. So the three kinds of measures of central tendency are mean, median, and mode. Okay, so let's talk about these things. Mean, the average. You've used that a million times. You use it all the time right now. If you take all of the values in a data set, you add them together and you divide by how many values you have, that's your mean, that's your average. Now, while the average is good in many situations, the average is also susceptible to what we call outliers. If you have a really high value or a really low value, it can really, adjust where the mean falls and might not be the best way to represent your data. That's why we have other measures of central tendency. Median. Okay, the median is the middle value in a list of numbers. So if I were to list my numbers together, 1, 2, 3, 4, 5, 5 would be my median, that middle value. Why would someone want to use the median instead of, let's say, the mean? Well, 1, 2, 3, 4, 5, the mean, the median are probably going to fall somewhat close to each other. But what if my values were 1, 2, 3, 4, 50? Okay, instead of just 5. That 50 would really pull the mean over. However, the median would stay as that middle number 3. Okay, so the median is less susceptible to the pull of outliers. So that's why sometimes a median might be a better situation. And then finally, mode is the value that occurs most often. So again, any of these three values could be potentially used to, describe what's happening with the data set. There are also some things called measures of dispersion. It really has to do with the spread or the scatter or the variability, I should say, of a data set. Think of it as spread, how far spread out they are. So the first one would be the range. Find the difference between the highest and lowest values. Okay, so that could tell you that most of your data falls within a certain region. But again, depending on if you have, outliers, those values that kind of fall on the outside, or, regular numbers, it might be affecting the range. Like if you look at the examples I used before, 1, 2, 3, 4, 5, most of your values are 1 unit apart, right? 1, 2, 3, 4, 50. Your values are mostly 1 unit apart, but that 50 makes the range go from 4 units to 49 units just because of that one number. That's why range isn't always the best. Variance is another way of looking at the measure or the spread, but the thing with the variance is that the way it's calculated is that things are being squared, so sometimes that's not always the best way of indicating the spread, and that's why eventually we're going to settle in on using the standard deviation. Okay, so you're going to end up seeing that oftentimes when we do our calculations. So approximating the standard deviation, what I want you to think of it as range divided by 6. You'll understand why 6 tomorrow when we get into actually something called normal distribution. So what does standard deviation tell us? Okay, so I'm going to show you different versions of each situation so you can start to understand a little how standard deviation is going to help as we start analyzing our data. Okay, so let's start with a big or a high standard deviation. What that's going to mean is that your data set is really spread out. Okay, so there's a lot of variation. So a lot of variation. Okay, your data values are very spread out. Okay, so your data is scattered. Okay. So then let's go into a smaller or a low standard deviation. Okay, the lower standard deviation means your values are going to be less spread out. So maybe your data set is going to look something more like this. Okay, so you can see the previous one had been very spread out. This one is not quite so spread out, so that would be a smaller or a lower standard deviation. If all values happen to fall where there is no standard deviation, that means there's no deviation. This is what this means. No deviation from the mean. What will that look like? That would literally look like one straight line of data points. All of your values would fall in the middle. Okay? So that's the idea. Higher standard deviation, more spread out. Lower standard deviation, less spread out. It's very unlikely that you're going to see one with no standard deviation. So let's take a look at some examples. Let's calculate some values. You're probably going to need your calculator, so if you want to pause the video and go get that, we'll take a look. So it says use the following distributions, aka graphs, to answer the questions below. So you have sample A and sample B, and already without even doing any analysis, let's talk about the standard deviation. Think of the values that I just talked about in the previous problem. Do you see how this first sample is very spread out? And that second sample is a little less spread out? It's more likely that this has a higher standard deviation in that first one. And again, I'll show you how to calculate an approximate standard deviation. So the mean's usually going to probably fall in the middle of your data set, especially these are considered, symmetric data sets, about equal on either side of that middle value. So we're going to say that the mean probably looks like in the first data set that it would come out to be 8. Okay, so this little X bar, that's a way of representing the mean without writing the word mean. Again, you don't have to use it. You could write the word mean. I'm just showing you some of the, the information. So the mean for group A would be 8. Okay, the mean for group B is also 8. So just looking at the means of these two groups, you're going to say, okay, well, those groups kind of seem similar. If you just look at those numbers, sure, maybe they look similar, but when you start looking at the actual picture, you can clearly see those data sets are not the same. What's the median of each distribution? Again, the median, the middle number, happens in this case to be 8 for both. So once again, you'd say, okay, mean and median are the same for both of these data sets, so they must be very similar, right? However, again, when you look at the picture, they're not going to be similar because of the way that the data is spread out. What is the range for each distribution? Range comes from taking the subtraction of the highest value minus the lowest value. So the range in group A, the highest value is 12, the lowest value is 4, so the range in that case would be 8. When you look at the range in the second one, the highest value is 10, the lowest value is 6, so that's a range of 4. So you can already see, now you're starting to see some differences in the way that these data sets behave. Again, what that actually means, you don't know until you have a context, but at least it gives you a way to compare the data sets. Which one has a larger standard deviation, and how do you know by looking at each distribution? As I said before, the one on the left is more spread out. That's why that has a higher standard deviation. The one on the right is less spread out. That's why it's going to have a lower standard deviation. How do we approximate the standard deviation? As I mentioned before, to approximate standard deviation, you're going to do range divided by 6. And again, it's not going to be perfect, but we're going to get, a good sense of how we can use that value to draw some conclusions today. So for sample A, if I want to approximate the standard deviation, I'm doing range divided by 6. That's 8 divided by 6, which comes out to be about 1.3 repeating. If I then go to sample B, my range divided by 6 comes out to be 0.667. Again, without a context, this doesn't have a meaning for you, but at least you can say, okay, well, while the mean and median of these data sets were the same, the range, the standard deviation indicates that there's some sort of difference between these two data sets. Okay? If you look a little lower, we're going to just talk about, more about distributions and kind of being able to give a name to them and compare mean and median and mode and stuff like that. So what we're going to end up studying tomorrow in something called normal distribution are things that we call bell-shaped curves. Okay, so the two examples actually that you just looked at before, those are examples of bell-shaped curves. Okay, they're basically symmetric on either side of the mean, the highest values in the middle. Okay, when you get to ones where they're not necessarily symmetric, that's when you start to get what we call skewed left or skewed right. Now, I will tell you, when I was in school, I used to always make this mistake. I would say, oh, all the data seems to be more on the right-hand side, so it's skewed to the right. No, right? Well, no, the answer is actually it's skewed left. So what you want to think of it as some sort of, I don't know, like... This is the weirdest analogy ever, but I almost think of it as like a little slug where the way the tail goes of the slug, that's actually the direction of the way that it's skewed. So the fact that this tapers off to the left, that's why this is actually skewed left. And the fact that this one tapers off to the right, that's why this one is considered skewed right. Okay, so it's the direction that it tapers off, not the side that contains the most data. All right, so We're going to get into more of like using some of these diagrams. And again, the goal is eventually to be able to draw some conclusions. So I'm actually going to skip ahead for just a second, and I want you to take a look at this situation. You have 4 different histograms, and we're trying to match these 4 histograms to the information below. Skewed to the right, skewed to the, 2 are skewed to the right, 2 are approximately symmetric. The mean is about 100 for all of them, and you have to be able to figure out the standard deviation. Okay, so let's take a look. Which ones seem to be symmetric? Which ones seem to be skewed to the right? So let me try to kind of like almost draw a general shape of what we see. Okay, the 2 that I'm drawing, I think you can see that those are mostly symmetric. It's not perfect, but you do have about the same amount of information on the left-hand side of what we think might be the mean and on the right-hand side. Whereas clearly when you look at histogram 2 and histogram 4, it seems like your data is more chunked to the left. But remember, again, it's about the tail being off to the right. So this one is approximately symmetric or bell-shaped, as we were mentioning before. This one's approximately symmetric. Okay, this one over here, this one will be considered what we say skewed right, because of the fact that it kind of trails off to the right-hand side. Okay, now we don't have to figure out the mean because it had said to us that 100 was the mean in every situation. So we know that our mean is at 100 in each of these cases. But the standard deviation is going to be different. Even though, again, maybe they look similar, standard deviation is going to be important because it tells you about the spread of the data. So how do we approximate standard deviation? It's approximately the range divided by 6. So we're going to go through each of these situations and we're going to ballpark range divided by 6. So our range, how do you figure that out? It's the highest value minus the lowest values. And again, these are still approximations. It's not going to be perfect. So our standard deviation in this first one is going to come from 125 looks like our highest value, minus 70 looks like our lowest value. Okay, divide that by 6, and you get a standard deviation in this case that comes out to be 9. Okay, in the second one, our standard deviation is going to come from range divided by 6, so that looks like about 145 minus 85 divided by 6, so that comes out to be something like 12. Again, these aren't going to be perfect, these are just approximations. In the third one, standard deviation looks like it's like 200 minus 0 divided by 6, so something that's kind of like close to 33. And then finally, the last one, standard deviation is about range divided by 6, so 325 minus 50 divided by 6, and that comes out to be about 46. Okay, again, they're not perfect. Look at the values that are actually in the table. Skewed to the right, again, means are not going to be different, so I don't have to worry about that, but has a standard deviation close to 10. Look at the 2 that were skewed to the right. Which one seems to have a standard deviation closer to 10? That looks like histogram 2. So histogram 2 is letter A. Approximately symmetric has a standard deviation close to 10. Our 2 on the left were the symmetric ones. The one that looks closer to 10, a standard deviation of 10 is histogram 1. Okay, so 1 is B. For C, approximately symmetric. So obviously it's going to have to be histogram 3. Standard deviation close to 40. It's not perfect. 33 is again in that vicinity. So C was 3. And then obviously D would then be 4. And again, we said standard deviation was close to 40. It's not perfect. Again, these are just ballpark figures. So I'm going to skip ahead to the next question because I want to get a little into how you actually use the data you're provided to draw conclusions. And I will tell you in advance, I love this question because I feel like it really helps to understand like how data helps drive conclusions. But I have no way in the world do I actually know how to say this Approximathids or something like that. So I'm going to strictly refer to these as compies. Just know that I'm talking about some sort of a dinosaur. Okay, so first, just take a look at the histogram. How would you describe this histogram? Does it seem to be skewed? Is it going one side or the other? Or does it seem to be approximately symmetric? I would say it seems approximately symmetric. Okay, it looks like about bell-shaped. It looks like half your data is maybe above, below, something like that. So let's figure out what does the mean probably look like here. I would say the mean probably looks like it's falling somewhere in the middle. Again, this is not going to be perfect. I'm just going to ballpark it based on what I see. But I'm going to say that the mean looks like it's maybe at 33.5 or something like that. Okay, so we're going to use that the mean is approximately 33.5. Okay, so the mean height of a compy is about 33.5 centimeters. Okay, so now as I go on further, let's start figuring out the standard deviation. So standard deviation, again, is approximated by doing range divided by 6. And the purpose of standard deviation is to tell you the spread of your data. And eventually you're going to be able to use that to draw conclusions about things that would be normal heights or abnormal heights based on what falls within a certain number of standard deviations or doesn't. So it looks like the highest value maybe is like 42. And I would say the lowest value kind of looks maybe like 25. Again, these are just ballparks. So let's say I do 42 minus 25 divided by 6. That turns out to come out to be a value of 2.8. So let's use 2.8 as our standard deviation. Okay, a normal interval. Okay, eventually when you get into higher degree stats classes, you're going to refer to this as a confidence interval. In particular, a 95% confidence interval is going to talk about when values fall within 2 standard deviations of the mean. And I'm going to show you exactly what that means in just a second. Okay, so a 95% confidence interval means data falls within 2 standard deviations of the mean. Things that are larger than 2 standard deviations from the mean or smaller than 2 standard deviations of the mean will end up being abnormal values for a situation. Okay, so that's kind of like one of the main things we talk about with drawing conclusions. Normal values versus abnormal. So state a normal interval for compy heights. That means you're going to take your mean, which is that 33.5. You're going to take your standard deviation, which we're saying is about 2.8. You're going to do 33.5 plus 2 times 2.8. Okay, what is that? That's the mean plus 2 standard deviations. And you're going to do the mean minus 2 standard deviations. So 33.5 minus 2 times 2.8. And that's going to give you the range of normal heights for a compy. So your highest value comes out to be 39.1. Your lowest value comes out to be 27.9. So a normal height for a compy, okay, falls between 27.9 centimeters, I think it was. Yep. And 39.1 centimeters. Okay, that's a normal height. So then basically what you could then draw conclusions from is like, when is a compy abnormally tall? When is a compy abnormally short? If it doesn't fall within this interval, that's an abnormal value. If it falls within this interval, that's a normal value. And again, we're going to discuss more of this when we get into drawing conclusions. So let's look at this last one. Is a compy that is 42 inches tall considered normal? 42 is not in that confidence interval, so no, that's an abnormally tall compy. So you would say, since 42 is not in the normal interval, and again, I want you to get in your head, normal interval means 2 standard deviations above the mean, 2 standard deviations below the mean. That's a normal interval for the situations we're going to be talking about. Since 42 is not in the normal interval, this compy is abnormally tall. Okay? So again, the purpose of today was starting to look at how data is organized so you can start